Thank you very much for waiting. The seminar is now ready to start. Good morning, ladies and gentlemen. I appreciate you taking the time to join us today. I'd like to extend a very warm welcome to you all and online participants. We'd like to start the seminar, Advanced Waste Management for Circular Economy and Energy Solutions, organized by Japan Environmental Facilities Manufacturers Association, JEFMA. I'm Yamamoto from JF Engineering Corporation. It's a great honor to be here at this seminar. Now I'd like to invite Mr. Hajime Oshita, Chairman of JEFMA and Executive Management Advisor of JF Engineering Corporation, for giving opening speech.
Good morning, everyone. Both here in the venue and joining us online. Thank you for attending today's seminar organized by Japan Environmental Facilities Manufacturers Association. This name is little too long, so we call it JEFMA. Yes. I'm Oshita from JF Engineering and now serving as the chairman of JEFMA. Yes. As you know, this summer in Japan was another record-breaking hot one. And heavy rains caused major disasters all over the country. We can't help but recognize that the impacts of climate change are becoming increasingly apparent. Given this sense of crisis, JEFMA is hosting this seminar at COP for the first time. We'd like to share some of our initiatives and to address these issues together with all those who are interested. We are especially honored that Your Excellency, Minister for the Environment, Japan, Mr. Asao, will take time out of his extremely busy schedule during international negotiations. Thank you very much for your presence. I'd like to express our gratitude to the Japanese government, the UNFCCC, CCC, officials, and all concerned members for providing us with these opportunities. Thank you very much.
Thank you. Now, I'd like to ask a remark from the Ministry of Environment. I'd like to invite the stage His Excellency, the Minister of Environment, Mr. Keiichiro Asao. Please.
Distinguished speakers and participants, my name is Keiichiro Asao. I'm the Minister of Environment of Japan. I am honored to provide opening remarks at this seminar, which aims to share recent developments in Japan's resource recycling industry. Thank you for inviting me to this special occasion. In Japan, the volume of waste skyrocketed during the post-war economic growth period, and people suffered from various hygienic and environmental problems caused by waste, such as odors and infectious diseases. Many people were engaged in trying to solve these problems, and the government decided that incineration is the key treatment method for organic waste, taking into consideration Japanese population density and weather conditions. Thus, various waste treatment facilities, especially incinerators, have been installed and in operation since then. And a top-class sanitary environment has been achieved in Japan, and actually, we are very proud of it. Nowadays, many countries are facing various waste management problems that Japan overcame in the past. Establishing appropriate waste management systems in these countries is crucial for a healthy environment. Also, proper waste management is important not just to maintain a sanitary and living environment. Landfilling or organic waste without proper treatment causes another problem: the emission of methane. Needless to say, methane is 30 times more powerful as a greenhouse gas than carbon dioxide, and appropriate waste management is very important for the world to achieve net zero. Many companies in Japan are well known for their excellent technologies in their area of resource recycling. One example of such technologies is so-called waste to energy, the generation of heat and electricity through waste incineration. I am convinced this kind of technology will contribute to the realization of SDGs by offering solutions to people suffering from waste-related problems while utilizing the energy generated through waste management. At today's seminar, I understand that people from Japan Environmental Facilities Manufacturing Association, or JEFMA, will share their latest technologies and experiences that contribute to both decarbonization and resource efficiency. I believe this will be of help to many countries facing waste-related problems. I conclude my remarks with my wish that today's seminar is very fruitful. Thank you very much, everyone.
Thank you very much. We are very honored this opportunity to have a remark from His Excellency. Now we'd like to have a photo session. All speakers, please gather in the center. Thank you very much for waiting, online participants. For the next agenda, I'd like to invite again Mr. Hajime Oshita, Chairman of JEFMA, for giving a presentation on development of waste treatment and greenhouse gas reduction in Japan. Please.
So I would like to express our gratitude はさっき言いましたから。I will now begin the seminar. First of all, I would like to give a presentation on development, waste treatment, and greenhouse gas reduction in Japan. Next, please. JEFMA was established in 1962 to provide excellent waste treatment facilities through improvement each other's technology. With 20 member companies, we have been constructed about 84% of municipal waste treatment facilities, maintaining high quality standards. Next, please. Let me explain from what JEFMA is doing. Today, we face two big challenges towards the realization of sustainable economic system. One is achieving a circular economy, and another is fighting climate change. These two challenges are closely connected, and we need solutions that achieve both at the same time. Looking at this diagram, JEFMA as a plant manufacturer handles the waste treatment parts shown in the red frame. Red frame. Oh, next one. Next, please. This one, okay. While promoting the 3 R's, reduce, reuse, and recycle, we focus on 2 things. Recycling as much as possible and getting the most energy from waste. This way, we contribute to both resource circulation and decarbonization. Next, please. In Japan, rapid economic and population growth led to increasing waste. This caused problems like bad smells from landfills, dirty water, and pest problems. Additionally, Japan doesn't have much land. We needed a solution for landfill site shortage. That's why Japan promoted the introduction of waste to energy and material recycling facilities from the perspective of sanitary waste treatment and volume reduction. As a result, nowadays, very little waste goes directly to landfills. Next, please. This slide shows merit. Waste to energy has various benefits besides reducing waste. Here are 6 important advantages. First is reducing final disposal volume. It can decrease waste by about 90%, which helps landfills last longer. Second is cutting methane gas. As you know, methane is 25 times worse than CO2 for global warming. When organic waste goes to landfills directly, it emits a lot of methane. Third is generating electricity. We can turn waste into clean power. Fourth is keeping cities clean. Appropriate waste collection stops unsafe dumping and makes cities clean. Fifth is to prevent plastic pollution, especially to the ocean. WT can safely handle plastics that can't be recycled. Last is clean the air. WT plants work with proper technology to clean the flue gas in Japan, so they can work safely in cities. Next, please. Let me share a real example from Vietnam. We built a waste-to-energy plant under Japan's joint crediting mechanism called JCM. According to calculations, this plant cuts the greenhouse gas by 70% over 15 years, even counting the CO2 from waste thermal treatment to comparing landfill. This proves that waste-to-energy really works for greenhouse gas reduction and fighting climate changes. Next, please. To achieve Japan's 2050 net zero target, JEFMA has developed its own technology development goals. We are focusing on methanation for the waste sector, aiming to complete demonstration and practical use in society by 2040, and continue to promote its expansion. Next, please. I'd like to introduce our latest developments. We are working on 2 exciting projects. One is finding ways to capture CO2 from waste-to-energy plants and put it to good use. The other is developing technology to turn waste into useful chemicals, like ethanol. Both technologies are now in demonstration phase, and we are working to make them ready for commercialization. Next page. Last page, maybe. We continue to contribute realization of global circular economy and achieving net zero by 2050 as our mission. Thank you for listening and all for your time. Thank you very much.
Thank you very much for the presentation. Next, I'd like to invite Mr. Soumya Bhattacharya, General Manager for Sales of JFE Engineering India, give him a presentation on JFE's solutions for circular economy, waste recycling technology, and CCUS. Please come to the podium.
Thank you, Mayo-san. Ohayou gozaimasu. And salam baku. And a very warm welcome to all my fellow COP participants. Before I begin my presentations, may I just express how wonderful it is to share this platform with such eminent dignitaries in Kuwara-san and Oshita-san. We're very excited to be here to talk to you and share with you our vision of achieving a net zero state in the world. And through this presentation, we're going to talk about waste recycling solutions. We're going to delve into the future initiatives of JFE in the area of carbon capture, utilization, and storage, or CCUS. And finally, we will take a look at waste to chemicals. So let's look at what this presentation has to say. I'd like to take you through an overview of the JFE group. We'll look at recycling solutions, waste to energy technology, and then delve into the features and benefits of CCUS and waste to chemicals. Now, at JFE, our solutions are dedicated to the foundation of life. It is towards preserving the gift of the planet to humanity for future generations. We build solutions that directly address our clients' decarbonization and sustainable development goals. So I'd like to now take you through a historical perspective of the JFE Group. Our roots lie in steel and shipbuilding. And over the years, we have brought in a rich and diversified experience of spanning over 100 years. Formerly, we were known as Nippon Kokan Limited, or NKK. In 2002, NKK merged with another giant in the steel industry, namely Kawasaki Steel Corporation. And this merger resulted into the formation of JFE Holdings Incorporated, our umbrella corporation, and a global Fortune 500 company. In 2003, our technology and EPC arm was launched, JFE Engineering Corporation. Today, JFE Engineering Corporation is one of the leading technology and EPC solution providers across the globe. It's interesting to note that in fiscal 2023, nearly half of our top line was achieved through solutions in the environmental sector, like waste to energy. But apart from that, we are also present as a major player in power, infrastructure, and energy. But JFE is not just a technology and an EPC player. We also partner with our clients to offer operation and maintenance services. We build customized recycling solutions, but that's not all. We go the extra mile to partner with our clients to offer investment solutions. For example, the Bakunin waste to energy facility that Oshita-san just mentioned, our role was not just a technology and EPC player, but we are also a co-investor in this facility. So we'd like to partner with our clients at various stages of their business to become a true stakeholder in their solutions. In 2023, our decarbonizing solutions achieved 11.5 million tons of CO2 emission reduction. This was built not only through our waste to energy solutions, but a whole host of other decarbonizing solutions, like waste heat recovery, biomass, geothermal, solar, and so much more. In fact, this achievement gives us the confidence to achieve our midterm fiscal 2024 target of 12 million tons of CO2 emission reduction, thereby solidifying our commitment towards decarbonizing the world. We're very, very glad to be here. We have wonderful memories of COP27 at Egypt. And I say this because it's only through a dialogue with like-minded allies that we can truly develop solutions that can take us towards our journey of achieving true circularity and a net zero state in the world. I'd like to now take you through some of our technology solutions, particularly related to recycling, waste to energy, and then we will look at carbon capture, utilization, and storage in this section. Let's talk about recycling for a moment. Why is that important? Because as we stand here right now, untreated waste is a menace to human life. There are many cities around the world where the air quality index is termed hazardous because of untreated waste. It pollutes our land, air, water, and is a general hazard to our ecosystem. So I think that today we are in a situation where it's all hands on the deck approach. And that is why we need to join hands here to be able to develop solutions that I'm going to elaborate on right now. At the heart of circularity lies recycling. And that's why I'd like to talk a little bit about our recycling solutions. At JFE, we build customized solutions for recycling separate streams of waste. For example, if you take up the biodegradable waste component, like food waste, we have digesters that process this food waste and produce biogas, which in turn can be used for producing electricity. In effect, we are recycling the biogenic CO2. Now, for the non-biodegradable component, we have separate individual streams of recycling. For example, we have PET bottle recycling. We have solutions for fluorescent lamp recycling, solar panel recycling, and so on and so forth. But also, this non-biodegradable component can be taken to a waste-to-energy plant to derive electricity out of that. But if you see, essentially the philosophy of treating such waste is centered around processing and disposal. But we believe that we can do more. In order to transition from processing and disposal and truly utilize the value of the carbon and the hydrogen in the waste stream, we need to transition from processing and disposal to utilization. And in terms of utilization, this is where advanced technologies like waste to chemical and CCUS really come into the fore. And that is what we are here to describe and share with you as to how we can unlock the value by utilizing the carbon in the waste stream. To start with, let's take a look at waste to energy. At JFE, we have 50 years of experience in constructing and operating waste to energy plants. And this is built on the simple philosophy that the incoming waste should be scientifically treated and disposed in an environmentally compliant manner. So the incoming feed, be it municipal solid waste or non-hazardous industrial waste, is then taken to our proprietary grate system and combusted in controlled conditions. The heat that is generated from combusting the incoming waste is then recovered and used to generate steam, turning a turbine for generating green electricity. Now, the benefits of a waste-to-energy plant are multifold, but chief amongst them is a contribution towards the quality of human life, a hygienic living environment. We also are able to generate electricity which is not dependent on fossil fuels. So you're not adding to the carbon cycle. And because we have more than half a century of experience, the plants are inevitably safe and reliable. Mature as though this technology is, we still believe that while we are generating green electricity from a waste-to-energy plant, the flue gas, which is released into the atmosphere, represents a loss of opportunity because it contains CO2, which you can capture. And that is where the advanced technologies like CCUS and waste to chemical can really make a difference and play a role. Maybe we should address a fundamental question. Why should we do this? Well, I think Oshita-san already addressed it, because waste to energy plus CCUS, while it can reduce the emissions, also addresses one potent area of minimizing methane emission to the atmosphere. And as we have seen, methane is one of the most potent greenhouse gases. And curiously, if you see the slide, it also contributes towards reduction of marine plastic pollution. And that's something I'd like to explain to you. Now, take, for example, any waste to energy plant where you have the flue gas which is let off into the atmosphere. This flue gas contains CO2, which if you are able to capture, you can store it, or you can utilize it for various end applications. For example, you can use this CO2 for agricultural use. It has mineral-related applications. You can also blend the CO2 with hydrogen to produce methanol. And methanol is the building block for producing plastic bottles, tanks, and even sustainable aviation fuel. So the utilization of this is multifold, but most importantly, you are able to capture and reduce the non-biogenic waste. You're able to enhance the circular economy approach, and you're effectively able to close the carbon loop. That is the advantage of this. And this is no longer just theory. What I'm talking to you has actually been practically established. At our Fujimi facility in Tokyo, where there's a waste-to-energy plant constructed by JFE, we have also implemented a carbon capture facility at a pilot scale. Would you like to see how this is done? Let me show you. At this facility, the flue gas, which would have otherwise been let off into the atmosphere, is first taken to a cooling chamber where the temperature is reduced. This is done so because at lower temperatures, the efficiency of CO2 absorption increases. After this, the flue gas is reacted in an absorber with an amine-rich solvent. This captures the CO2 in the solution, and it is then taken to a regenerator where the CO2 is released by means of increasing the temperature. The CO2 that is recovered has a purity fraction in excess of 99.5%, and we are able to recover up to more than 90% of the CO2 in the flue gas. Why is this important? Because with a solution like this, you're able to achieve a negative carbon emission status in all waste-to-energy plants. Thus, this is truly a revolutionary technology in terms of enhancing the carbon emission reduction and circular approach. And talking of a circular approach, may I just now take you to the pinnacle of our next generation technology, which is in waste to chemicals. Now, we saw that by the CCU solution, we are able to capture the CO2, reduce the emissions. But my question to you is, what if we could eliminate the emissions altogether? And what if we could also reduce the fossil fuel usage? With our waste to chemical solution, we are able to process the incoming feed like municipal solid waste, like plastic waste, like industrial waste, and we are able to create syngas. Now, this syngas is the foundation block for creating varied applications. For example, you can create plastics, you can create sustainable aviation fuel. You also have the option in future to create free hydrogen from this. As I mentioned, the heart of the system and the solution lies in producing syngas from various feed. You're not dependent just on a specific feed, but you can process municipal solid waste, industrial waste, or various other feed to produce syngas. Now, this syngas can then be taken through a biorefinery process to produce ethanol, or a catalytic process to produce methanol. And these are the foundation blocks for producing plastic, or aviation fuel, or hydrogen, as I mentioned. So let me now explain to you how is it that we are able to achieve this, and what's really different about our solution. Like I mentioned, the key is producing syngas, because once you get that, you're able to produce all the other requisite materials. Now, JFE has the experience of over 20 years in construction and operation of gasification systems. So with this experience comes the know-how to produce syngas in an efficient and a reliable manner. Now, why is this different and how is it different? It's different because unlike other systems, this is a pure oxygen gasification reaction. And what this does is that the energy content in your syngas is substantially higher than other forms. So techno-commercially, this becomes a very lucrative proposition. What we do is the feed, which is municipal solid waste or plastic or industrial waste, we introduce it to a high temperature gasifier with the temperatures reaching maybe about 1600 degrees or 2000 degrees centigrade. At such high temperatures, the carbon in the incoming waste is gasified in a partial oxidation means. The gas cracks the organic compounds and melts the incoming inert and metals. Now, post this, we rapidly cool by water quenching so that we are able to avoid the reformation of complex compounds. This results into a formation of syngas, which is comprised mainly of hydrogen, carbon monoxide, and carbon dioxide. This syngas is then cooled and scrubbed for ensuring that we remove sulfur and other impurities. And once we have a clean syngas, it has various end applications, as I just spoke to you about. The inert material that is left is then homogenized and cooled, essentially undergoing what we call as a vitrification process. And then after the vitrification, the slag that is left has various end applications. So you're essentially looking at a zero waste solution with a value-added syngas produced out of multiple input feed. Like I told you that the advantage of the system is A, a high energy content in the syngas. B, the flexibility to use various input material like municipal solid waste or industrial waste. But most importantly, with an entity like JEFMA, you have a know-how that spans over 2 decades, which is able to deliver you a reliable and efficient solution. Now, the Japan government, in a bid to provide an impetus and incentivize decarbonizing solutions, have established a 2 trillion yen fund in order to promote decarbonizing solutions and future initiatives like what I just mentioned to you. Under this fund, JEFMA has taken on the responsibility to construct and implement a waste-to-chemical plant at our Chiba facility by 2025. This is a prototype plant, and post-establishment of the prototype plant, we're looking to partner with global entities to offer the waste-to-chemical solution at a commercial scale worldwide. And this brings me to a conclusion of my presentation. We believe that in order to solidify our commitment towards achieving a decarbonized and a net zero state in the world, the solutions like CCUS and waste to chemicals are extremely pivotal to strengthen our journey between now and achieving a truly circular economy and net zero. My name is Soumya, and here at JEFMA, we stand just for the Earth. Thank you so much. Really appreciate it.
Thank you very much. As a presentation, JEFMA can contribute to the net zero and the circular economy through waste to chemical and CCUS. We are committed to implement this revolutionary technology. And next, I'd like to invite Mr. Michi Kuwahara, Representative Director President of Chief Operating Officer of Canada Corporation, for giving a presentation on achieving circular economy by diverse waste management technology and CCUS.
Thank you for introduction, Yamamoto-san. Hello, everyone. Thank you for being here today. My name is Michi Kuwahara. and I am COO of Canadavia Corporation. Today, I'd like to introduce our company's waste management initiatives for a circular economy. I would really appreciate it if you could get well understanding who is Canadavia, what technology Canadavia can provide, and how Canadavia's proposal of waste management system can contribute for a circular economy. I'd like to start by introducing a company. Since 1984, we have been operating under the name of Hitachi Zosen. As part of growing a global company and build a brand which reflects our company's philosophy. This October, we changed the company name to Canadavia. The new brand name Canadavia is blended from Japanese verb kanaderu, meaning play music in harmony, and Latin word meaning way or method. Now, we have decided to take a faster step to grow under the new brand concept of Canadavia, taking on the challenge through the power of technology to create the world that lives in balance with nature. These are our business field. The ideal position of a company is as a solution partner, contributing to the realization of a sustainable, safe, and secure society. We are developing these three business areas: resource circulation, decarbonization, and creating safe and prosperous cities. We have endorsed TNFD recommendations, and as early adopter, we issued a TNFD report this October, focusing on waste to energy and biomass power generation business. We position environmental resilience, maximize environmental resilience as a materiality. Based on that, planetary boundary concept, we aim to keep environmental impact of our business activities and entire value chain within the range of original environmental resilience of each country and regions. This is our vision of resilience eco-society. And this is our history of waste to energy business. It started in 1960 with a technical collaboration with Fonlo, waste to energy manufacturer in Switzerland. In 1965, we built first waste to energy plant Osaka in Japan. In 2010, we acquired Innova and also integrated. Since then, we continue to expand our waste to energy business worldwide. This map shows the number of waste to energy plant ordered to Canadavia Group, including licensees. We got ordered more than 1,500 plants worldwide. And this is the largest global market share. This is Kyoto South Green Center, which is not only waste to energy for energy recovery, but also combines material recoveries and also methane fermentation. And this is our reference plant in Dubai. This is one of the largest waste to energy plant in Dubai. And the Dubai government has already declared a policy of use of clean energy, including waste to energy. The construction of this plant significantly contributes the policy, Dubai government policy. And this chart shows the relationship between GHG emissions, proper waste treatment, and a push toward a circular economy. Landfill sites discharge a significant amount of methane from organic waste. There is a concern about the discharge from plastics in open dumping into the ocean. Landfill was the main disposal method up until around 1950s, but in 1960s, we introduced the thermal waste treatment plant, improving public health and also reducing environmental load. Now, our challenge is net zero GHG emission by using waste to X, converting the waste into energy and resources, and CCU, carbon capture and utilizing. Let's keep this. And the waste to X technologies. Waste to X technologies we are working on. First, pyrolysis, gasification, reforming technologies. Through these technologies, the waste of various composition is converted into gases, such as hydrogen and carbon dioxide. These gases can be used in a wide variety of applications as a substitute for fossil fuels and low chemical materials. Currently, we aim to fiber recycle some of the massive amount of textile waste generated worldwide from fast fashion. Secondly, this is biomethanation technology. Generally, biogas contains about 60% methane and 40% CO2. But this technology increases the methane concentration through the action of microorganisms. These photo and diagram are of waste treatment facilities in Switzerland. Hydrogen generated from the electrolyzer with energy from waste incineration plant and sent to a bioreactor. And then hydrogen is then methanated with CO2 in the biogas from sewage treatment plant. The produced gas is upgraded and supplied to the regional gas grid as biomethane. And next one is bioethanol production technology. From mixed waste, the suitable waste for alcohol fermentation is extracted. And then extracted such as food and paper waste, and then fermented to produce bioethanol. Furthermore, fermentation residue can be used for methanation process. Therefore, this is a technology producing two types of biofuels. And then this produced bioethanol can be used in a wide range, various applications as a substitute for fossil fuels. For example, as a raw material for biojet fuel or substitute for gasoline. This is a demonstration plant for waste treatment plus CCU in Japan. We installed CO2 recovery unit and catalytic methanation unit at waste treatment plant in Kanagawa Prefecture. This is the largest methanation plant in Japan at the time and succeeded in producing e-methane. This is the first methanation plant in the world using CO2 from waste treatment plant. With these initiatives, we have found a way to achieve net zero GHG emissions by using CCU for waste that simply cannot be recycled. And fifth, our demonstration of waste to energy plus CC in the UK. At this facility, up to 1 ton of CO2 is captured per day. At this moment, in the UK, large-scale projects for hydrogen conversion fuel and CCS are underway. Next, I would like to introduce our challenge in the latest national project, including subsidies from Japanese government. The development budget is approximately 125 million US in Green Innovation Fund project. This is a development of waste treatment technology to increase the efficiencies at separation and recovery of CO2. Normally, we use ambient air, but this technology uses recirculated gas with high CO2 concentration. As a result, the concentration of CO2 in the exhausted gas is 3 times higher than the normal process. Then we can achieve high CO2 recovery and also reducing exhausted gas volume. This technology enhances waste to energy plus CC, greatly contributing to achieving net zero GHG emissions. So finally, we propose a waste management system that combines our new waste management and decarbonization technologies. For example, offshore wind power, water electrolysis, methanation, and others. We are showing this new waste management system model in the Japanese pavilion just over there. So just please stop by. Applying Canadevia's technologies, we will transform wind, seawater, and waste into renewable energy and resources, creating a new way of life that not increase GHG emissions. Now, I would very appreciate it if you could get some sense how Canadavia can contribute for a circular economy. As you can see here today, we can do a lot, but it's so obvious. Just a single company's effort is not enough at all. The way to achieve circular economy is still so far away. And therefore, we really would like to work together with you and also connect with you all. So I strongly believe we need to connect and we need to collaborate to accelerate the process and to find a more excellent way for circular economy. Thank you for listening.
Thank you very much, Mr. Kuwahara. Through the presentation, we can expect the comprehensive waste management system by the technology. And we can say the system get ready to the world. So next, I would like to move on this presentation, performance of trans heat container system for energy saving and reduction of CO2 emission by Mr. Yoshihiro Iwai, Senior Expert, France and Machinery Systems Headquarters of Sankey Engineering Corporation Limited. This will be given by video presentation.
皆様、はじめまして。ジャパンパビリオンにお越しいただきありがとうございます。本日は三貴工業が保有する蓄熱技術トランスヒートコンテナについてご紹介いたします。トランスヒートコンテナは主に200度 C 以下の排熱を回収し、時間と空間を超えて利用する技術です。詳細につきましては、こちらの AI アバターにお願いします。それでは最後までお付き合いください。
Hello everyone. Today's presentation will focus on the performance of the trans-heat container system in terms of energy savings and CO2 emission reduction. The trans-heat container is a registered trademark of Sankey Engineering. This technology was originally developed in Germany in the late 20th century, and we acquired the licensing rights in 2011. The trans-heat container, or THC system, adopts a latent heat storage method. This utilizes phase change materials, or PCM, for offline heat supply systems. The main challenge in utilizing unused thermal energy lies in overcoming the time and distance barriers between heat sources and potential users. For instance, waste heat from factories or incineration facilities can serve as a thermal source. Meanwhile, hospitals or office buildings could benefit as heat users. However, there is often a mismatch in timing or location of heat availability. Our solution is the trans-heat container, a system that transports heat via containers filled with phase change materials. These containers are transported by vehicles between the heat sources and users. The system includes heat exchangers for both the source and the user, as well as multiple trans-heat containers and a transport vehicle. We will now discuss our practical experiences with implementing this technology in real-world applications. We have selected two phase change materials, or PCM, the system: sodium acetate trihydrate and erythritol. The first reason for this choice is their melting points are ideal for capturing and reusing unused thermal energy. The second reason is safety. Both materials are food additives, making them non-toxic and non-hazardous. Additionally, they are commercially available. Sodium acetate trihydrate has a melting point of 58 degrees Celsius. This allows for the efficient use of most unused thermal energy up to 90 degrees. From 2004 to 2006, we developed the use of erythritol as a PCM in Japan. Erythritol has a melting point of 118 degrees, and although its heat source is limited to 160 degrees, the stored heat can also be used for cooling. Furthermore, it has a higher heat capacity than sodium acetate trihydrate. This figure illustrates the large capacity type container. Inside the container, PCM and oil coexist. However, when separated by their different specific weights, PCM is denser than oil. During heat exchange, thermal oil is introduced into the bottom of the container through an inlet pipe. The oil droplets pass through the PCM layer. During heat storage, high-temperature oil melts the PCM by transferring heat. For heat release, low-temperature oil absorbs heat from the PCM. This causes the PCM to change from a liquid back to a solid. The vast surface area of the oil droplets allows for a high rate of heat exchange. In the video, the white solid represents the PCM, while the transparent layer above it is the thermal oil. During heat storage, hot oil is supplied from the bottom of the container, causing the PCM to transition from solid to liquid. During heat release, low-temperature oil is introduced from the bottom. This turns the PCM back from liquid to solid. The next figure shows a standard capacity type container. The large capacity model isn't suitable for Japan due to road size limitations, which makes it difficult for semi-trailers to operate. To address this, Sankey has developed a smaller, more simple container that works with detachable body trucks. This container uses a shell and tube heat exchanger, where the heat medium does not come into direct contact with the phase change material. The heat exchange surface area is limited by the tubes. This results in a lower heat exchange rate compared to the large capacity type, and a greater pressure drop within the pipes. Therefore, this simplified container has some disadvantages compared to the larger model. So, why have we developed this type? It was designed for smaller vehicles, making it easier to set up in typical waste collection containers. Small vehicles can operate without being constrained by traffic regulations in Japan. The container doesn't need to remain horizontal, allowing for simple loading and unloading. Additionally, there are no special driver's license requirements for these vehicles. Many of our clients are industrial waste disposal operators, with incinerators as heat sources and waste collection vehicles. The standard capacity container can easily be integrated as an attachment to these vehicles. This kind of customization is crucial for making the system practical in Japan. This section covers the large capacity type. Let us begin by explaining the transport type as a reference. We have installed the system at 4 locations in Japan. 3 of these are transportation types, while 1 is stationary. In terms of PCM usage, 2 sites use sodium acetate trihydrate and 2 use erythritol. The maximum transportation distance is approximately 28 kilometers, with a delivery time ranging from 30 to 50 minutes. This section introduces the stationary type, which is used when heat needs to be stored and utilized during different time periods. Let us introduce the stationary type system at a mineral water factory. We installed 2 trans-heat containers using sodium acetate trihydrate. The heat sources include various heat waste from the production area, the primary source being high-temperature compressed air. It is then used to heat the office space. This storage system operates continuously and has recorded 5,062 gigajoules of heat over the year between October 2008 and September 2009. This figure illustrates 48 hours of operation. As shown, during production, most of the reclaimed heat is used directly, represented by the green bar in the upper section. The blue line indicates the heat released from the trans-heat container, or THC, while the pink line represents the amount of heat stored in the THC. During production pauses, the boiler works harder to compensate. This section explains the standard capacity type. We have installed the standard capacity type at 3 sites in Japan. 2 are transportation types and 1 is stationary. Regarding the PCM used, 1 site utilizes sodium acetate trihydrate, while 2 use erythritol. In Toyama, for example, the system is used as a heat source for air conditioning in a tomato plant factory. During summer, the system generates cold water at 15 degrees Celsius by using an absorption chiller. This section details a case study for the standard capacity transport model. This photo was taken at a demonstration test facility in Mie Prefecture. The left is the heat storage facility, and the right is the heat recipient facility, with a distance of about 11 kilometers between them. The heat source comes from excess steam generated by incineration facilities, using erythritol as the PCM. Each container has a heat storage capacity of 500 kilowatt-hour and is used to heat water. The site test was conducted from May 2014 to January 2015. During this period, 161 times heat supply cycle tests were completed. After this test, Mie Chuyo Kaihatsu, a partner developer, converted the test facility into a commercial one. Since October 2015, the facility has been in full operation, with 217 heat supply cycles performed. As of 2024, these facilities continue to operate commercially. This section explains the stationary type model. This facility has been operating with the latest technology since 2022. The system is integrated into a waste incineration facility, running 16 hours daily. The system stores heat in the daytime when the facility is operated and releases it at nighttime when the facility is idle. While the incineration facility is active during the day, the system simultaneously supports road heating and heat storage depending on demand. 2 trans-heat containers are connected, each with a capacity of 350 kilowatt-hour. To conclude, latent heat storage provides an efficient and stable heat supply for hot water and room heating. The transport system also contributes to reducing CO2 emissions. However, the feasibility of the system is influenced by factors such as traffic regulations, road conditions, and driver costs. If autonomous vehicles become authorized in the near future, the viability of the system will significantly improve. We are excited about the potential of driverless vehicles. This development has been supported by the Ministry of the Environment.
我々は三期工業、みんなの快適を形にしているのである。
でもさ、地球にも快適じゃないとね。
省エネは大事。
いっそエネルギーを作るとか。
再生可能エネルギーってやつね。
水の再利用もやってるよ。
自動化で人手不足も解消。
人も快適、地球も快適。
どっちもやるのが
サステナブル。
快適をサステナブルに。三期工業です。
Thank you for your attention. Please visit our homepage, where this presentation and more detailed data will be published.
Thank you very much for watching. This is the end of our seminar. So as we explained through the seminar, the JEFMA leads the next generation technology for Japan, from Japan together with established and experienced technologies. So please remember of JEFMA's name and for providing the technology to your country. Thank you very much.